Everyone, I'm Hongzhan from Sicun. Today I will talk about our work comparing computer functions using auto distribution analysis. There'll be no foundation model in the next 10 minutes. So first, I'll provide some background on controller functions. So controller functions, or CBFs, are a powerful tool to certify safety for control system. Let's consider a system with dynamic f-depth with an unsafe region. The CBF are a scalar function over the state space with whose zero level set is the safety boundary. And let's denote its super zero level set by C. So by definition, this set C must be disjoint from the unsafe region of the system. And for every state within it, there always exists control that satisfies this lead-root condition. And therefore, by Nagumo's theory, it is guaranteed that this set C must be safe and control invariant. And for the state that are neither in C nor XU, they are the state that will inevitably enter the unsafe region. And constructing controller function candidates are quite complicated for complex systems, and therefore people have turned to data-driven neural CBFs. For instance, I'm showing here the dynamic optical avoidance, the multi-robot control, as well as the jet stabilization. And typically, the training for CBF is performed over the label sets that are provided, where we also optimize to enforce the lead-root condition to impose invariance. And here arise two concerns. So first, any mislabeled samples could impact the learning quality, and those actual labeled data sets may be unlimited. And therefore, it is important to effectively leverage unlabeled data while avoiding mislabeling. The standard annotation procedure is to forward simulate these unlabeled samples, and then we just trust the predictions of those neural models. But apparently, the strategy suffers if the model has not yet generalized. So in our recent eCRO paper, we propose incorporating auto distribution analysis. And the set we consider is to learn from a fixed, sparsely labeled data set. And our key insight here is that to annotate an unlabeled sample, we should check whether there exists a control that can lead to a state that's both safe and in distribution. And therefore, the annotation should be dependent on not just the predicted safety score, but also some calibrated OOD scores. And intuitively, we want to validate the expansion of those safe and unsafe distribution using OOD detection. So implementation-wise, we followed earlier work about cost-sensitive binary classification with rejection to do the OOD detection. So more specifically, the cost-sensitive classification assigns distinct misclassification cost using thresholds. So here in this work, we train a two-headed network using complementary thresholds C and 1 minus C. So the intuition here is that these two heads are optimized to intentionally overfit to the data manifold in opposite directions. And therefore, the conjunction of their high confidence regions sharply align with the true data support. And therefore, for the inputs, the inputs for which the two heads disagree are rejected as OOD. And to accelerate this control search, we also train an actor model to predict the maximally safe in-distribution control. So intuitively, if even under the safest control, we cannot get to a subsequent safe state, then it's necessary to check any other less safe controls. And here's our actor training objective. So we first just maximize the subsequent state safety while ensuring it will remain in distribution. And lastly, this is our CBF training objective. It's pretty much aligns with the prior work while leveraging the proposed annotation and the actor model. So some experimental results. So we have more quantitative results in the table comparing the base sample here. I will just provide some interesting results to me. So first, this is an ablation study to demonstrate the importance of a label set. So here, it's a toy system for bicycle vehicle with static optical avoidance. and we plot the empirical performance against the training iteration. And the ledgers here are the sizes of labeled and unlabeled sets. So from the left part, we show that like with the fixed labeled sets, learning could be stimulated using small amounts of unlabeled data. This is justified by the performance gain from increasing the unlabeled set size from 25 to just 800. In the right part, we show that with fixed unlabeled data, here exists a threshold to label set size, beyond which the learning becomes indifferent. And we also perform Howard experiments to validate our method in both single agents and multi-agent settings. We provide more quantitative results in the paper, but we just show the videos here. So here, the training is performed solely on real data. I think for the left one, we only use about like 20 minutes real data, and we're able to achieve comparable performance with many baseline sources. And yeah, and for the right hand, this is our new case submission, case paper, doing multi-agent with our method. But there's issue with it. So like when constructing our 20-minute offline data, we have to purposefully collect some failed scenarios, which we really didn't like. I mean, we may break our robot. So we have been also looking into this problem of one-class classification and hope that like how we can learn this control environment landscape using only expert demonstration. And the idea will be to, avoid entering the distribution. And also, we're also like everyone's doing large models. We are giving that a try as well. So we are thinking to how, in the process of fine-tuning large models, how we can learn some barrier functions in the latent space to enhance control safety. This is what we're doing. And this latent dynamic modeling was mentioned by Professor Andrew. This has some promises in other domains. So we are giving that a try as well. And just to conclude, utilizing unlabeled data is beneficial to learning control barriers, and OOD could be important.